So hello again, this is Galen Pickett, Cal State Long Beach, Physics 151 online. So today I want to talk about determinism. Chapter 3, Section 10. This also relates to, up here in Chapter 2, the iterative prediction of motion. They are very closely related, so those are two sections I want you to pay close attention to. So there's this cycle of taking some input. So I know where is an object, where it is. So I know what its r is, I know what its initial momentum is, and I want to find out where is it at any other time. Well, I'm going to need to know what is the force as a function of time on the object, and to find out where it's going to be a short time later delta t, there are a couple of, we're just going to use the momentum principle, the definition of the average velocity, and then the position update to find out where the object goes. So, momentum principle tells me if I'm given the initial momentum and the initial position, P final, which is equal to m times v final, is equal to m times v initial, plus whatever force is being applied times delta t. So that is just the momentum principle. Together with that, I can just find out what the final velocity there is going to be at the final time. I just divide everything by m. I get v final is equal to v initial plus f divided by m times delta t. So if I'm given what the initial velocity is, I can tell you what the final velocity at the end of delta t is going to be. Now, the average velocity. The average velocity is the thing that tells me where the object actually goes. So v average is equal to 1/2 v initial plus v final. Well, I know what the final velocity is there, so v average is then equal to 1/2 v initial plus, here's my expression for what the final velocity is, I'll just put it in, v initial plus f over m times delta t. So what I get is my average velocity. If I add these two vectors together, I get 1/2 times 2 times v initial plus f divided by m, those are vectors, delta t times 1/2. So the average velocity, if I figure out that just tells me my average velocity is equal to my initial velocity plus 1/2 f over m times delta t. So this quantity here, as long as I can figure out what it is, I can tell you how the velocity changes. This is something like a velocity update idea. And then position update tells me that r final is equal to r initial plus delta t times v average. And those are all exact expressions as long as the force isn't changing too much. So I could just put that in. R final is equal to r initial plus delta t times my average velocity is equal to my initial velocity plus 1/2 f over m times delta t. And that's something that you've used many times before, this momentum principle, average velocity position update. But let's see what it looks like graphically. So here's my origin, so 0, 0, 0. Here is, say, the initial position of this object, r initial. And let's say that that is the initial velocity of the object, say times delta t. So if I was going to tell you where is the object at the next delta t, it would just be there. If there's no force acting, then it would wind up there, and there, and there, and there. You just keep adding v initial times delta t, tells you where the object goes from one time to the next. But that's not what's happening. I've got a force that's acting, and let's say that my force times delta t over 2m is some vector which is just a constant vector I'm going to point downwards. So there is how the initial velocity gets turned into the final velocity. So instead of winding up here, where I would be if there was no interactions, I wind up at a smaller spot with a smaller position here. So there is actually what is how I would update my position. And now I can use this as my initial position and that as my initial velocity and do this whole thing over again. I add a little bit to my position, I wind up here. I add a little bit more to my position, so there's my new initial velocity. There's this same change in the velocity is the same from one time to the next right there. So let's say this is what a constant force would look like. And I think you can see that this position, the trajectory that's being mapped out, is one of these parabolic trajectories as long as f is a constant. And what it means is as long as I tell you what the initial position is and what the initial velocity is, there's no further, there's no freedom anymore in the system to tell you exactly what's going to happen. And that is the sense in which something which really bedeviled philosophers and physicists alike in the mid-19th century, this idea of mechanical determinism. It's the idea that if you know enough about a physical system, and you are a physical system, I'm a physical system, I'm made out of atoms, you're made out of atoms, if I know enough about this mechanical system, so where every atom is and how fast it's going, I can predict everything about its future behavior. And so I can predict why I'm going to make a blue mark that's a bunch of wavy things. I could predict, at the beginning of the semester how you're going to score on all the homeworks. I can take all of the freedom out of the physical system. My own personal opinion is that mechanical determinism is still a significant problem for philosophers and for physicists. I don't think that we have escaped really this mechanical deterministic box, but you use this kind of determinism in video games all the time. Here's an example of it. Here's an example of a video game that you use where this cycle of where is the object, how fast it's going, from one time to the next, change how fast it's going, figure out where it goes. It's exactly this Angry Birds game. So the only thing that you have to control here is the initial velocity of the bird. That's controlled by how you pull back this the slingshot. The initial position of the bird is set by the game itself. So you only have one thing to set. What is that initial velocity? And there was my initial velocity. Almost got it. So if you look from time to time, the game actually tells you where are the dots and how that's being changed by the momentum principle. This is the dot-crumb trajectory that you can get from an actual measurement. So the game mechanics, the physics mechanics in all the video games that you like playing are exactly doing this mechanical deterministic loop.